A pharmacist mixed some 10% saline solution with some 15% saline solution to obtain 100 milliliters of a 12% saline solution. How much of the 10% saline solution did the pharmacist use in the mixture? Okay, so we have a 10% solution. Let's call that T. And we can draw a few bubbles coming out of it. And we'll have our 15% solution. Let's call that F. And we're going to pour these two into another cup. Let's call that our mix. And we need to figure out how much of the 10% saline solution, so our T, how much of that did we pour into the mixture? So these mixture problems can seem confusing and complicated, but the goal is just to first visualize what you're doing, and then second, try to make as many equations as you can based on this information. What does it mean to be a 10% saline solution? That means that the amount of salt in T, which is our 10% saline solution, the amount of salt in there is going to be 10% of the amount of liquid in there. So saline just means salt. So the amount of salt in T is going to be 10% of the liquid in there. Similarly, the amount of salt in F is going to be 15% of the amount of liquid. And we also know that we're going to mix these. So the amount of salt in the mix is going to be equal to the amount of salt in T plus the amount of salt in F. And in a similar way, since we're mixing these two solutions, the amount of liquid in the mix is going to be equal to the amount of liquid in T plus the amount of liquid in F. Let's see if we have any other information in our problem. So we're mixing our 10% saline solution, that's our T, with our 15% saline solution, our F, to obtain 100 milliliters of 12% saline solution. Okay, so our mix over here is going to be 12% saline. So we can make an equation with that. If we know it's 12% saline, that means the amount of salt in the mix is going to be equal to 12% of the amount of liquid. All right, we just wrote down a bunch of equations using the information in our problem. It's a real-world situation, so using words in our equations instead of variables, that helps us get a better understanding of what's going on, as does drawing a picture. So let's see if we can now introduce some variables. So the question's asking how much of the 10% saline solution did the pharmacist use? So in our equations below, that's referring to this amount of liquid in T. So how much of the liquid is in there? So we don't know that, so that's a variable. Let's call that baby T. So that's what we need to solve for. And similarly, let's go ahead and call our amount of liquid in F. Let's call that lowercase f. We see those two variables in another equation. So we have the amount of liquid in T and the amount of liquid in F. And if you notice, The left side of that equation says the amount of liquid in the mix. Well, we actually know what that is. Our problem tells us it's 100 milliliters. So we can replace this with 100. And that shows up on this side. And another thing you might notice is that we have two equations for the amount of salt that's in the mix. The bottom equation tells us that the amount of salt in the mix is 12% times 100. So we can actually substitute that into our first equation. So we can place 12% times 100 onto the left side of this equation. Also, you might notice that we have amount of salt in T in this equation, but we know what that's equal to. That's 10% times T. So we can write that in there. So this amount of salt is going to be 10% of T. Similarly, the equation has amount of salt in F, and we know what that's equal to. That's equal to 15% of F. So we can write that in there. 15% of F. So you might notice at this point that we don't know what T and F are, so what we're trying to do is find a system of equations so we can solve for T and F. And we have that. We have an equation right here with T and F, and we have another equation with T and F. So let's bring that down and try to clean this up. So 12% times 100, that's our first one, is equal to 10% times T plus 15% times F. And our second equation says 100 is equal to T plus F. So let's rewrite this system using decimals instead of our percents. So if we have 12% of 100, that's the same as 0.12 times 100, which is equal to 12. So we can just place 12 on the left side, and 10% times T is just 0.10 times T, and then 15% is 0.15, and we multiply that by F. The second equation, we can just keep the same. So the hard part is done. We've looked at our word problem, found our series of equations, and then created some variables. That allowed us to make our system of equations. Now we have our two options, substitution or combining. So let's go ahead and do substitution on this. So on our second equation, I'll subtract T from both sides. That gives us 100 minus T equals F. So we solve this equation for F. We know F is equal to 100 minus T. So we're going to substitute that into our first equation. So that gives us 12 equals 0.10 times T plus 0.15. And then we'll make our substitution for F. That's equal to 100 minus T. And the reason that I made this substitution for F is that the question's asking what is the value of T? How much of that 10% solution did we put in the mixture? So now we have an equation with just T, and we can get straight to the answer. Okay, let's work through this step by step. We'll use the distributive property to multiply that 0.15 into each piece on the inside. So we'll get 0.15 times 100 minus 0.15 times T. We'll rewrite this to group our T's together. So we'll have 12 equals 0.10 times T minus 0.15 times T. And then we'll add our 0.15 times 100. Now we can simplify this. So we'll have 0.10 minus 0.15. That is negative 0.05 T. And then we have 0.15 times 100. That gives us just 15. So when you multiply a number by 100, you may know the trick that you move the decimal point 2 spots, and that's your answer. So 0.15 times 100 becomes 15. All right, now we want to get t by itself. So we'll subtract 15 from both sides. On the left side, 12 minus 15 is negative 3. And on the right side, we just have our negative 0.05 times t. Now we divide both sides by negative 0.05 because we want to get t by itself. And on the left side, we have negative 3 divided by negative 0.05. We can use our calculator in this case. So we have negative 3 divided by negative 0.05, and that gives us 60. So we have 60 is equal to t. And remember, t was the amount of liquid in our 10% solution. And the question asked, how much of our 10% solution did the pharmacist mix? So that would be 60 milliliters. So this problem took a lot of work. First, we visualized what was happening. We had our two solutions, our 10% and our 15%, and then we mixed them. And we had some new terms to learn. We had to know what 10% saline meant. So that meant that the amount of salt in tea was 10% of the amount of liquid in there. And as I mentioned, with these problems, these mixture problems, the strategy is to write as many equations as you can and then try to find the connections between them. We knew that the amount of liquid in tea, that was unknown. That's what the question asked for. And similarly, we knew the amount of liquid in F was unknown. So we created those variables, and then we saw that those variables were in other equations as well. So these questions take some thinking. You have to really understand what is this word problem talking about, and what are the relevant equations, and then you have to see how these equations connect. Now we're going to move on to a new concept. Andy's average driving speed for a 4-hour trip was 45 miles per hour. During the first 3 hours, he drove 40 miles per hour. What was his average speed for the last hour of this trip? Okay, we're going to introduce a new formula. That is rate times time equals distance. So rate, you can think of as speed. For example, if you're in a car, it might be going 50 miles per hour. And the time, you could say that it's going for 2 hours. So if you drive 50 miles per hour for 2 hours, you're going to end up driving 100 miles. So we get that from 50 times 2. And if you're familiar with unit conversions, you know that our units, hour, cancel. So we're left with just miles. Let's consider another example. Let's say you're playing a video game where you're shooting zombies. And let's say that you shoot 200 zombies per hour. And you do that for 3 hours. Again, we can multiply 200 times 3, and that'll get us to 600. And our units, hour, cancel out, meaning we just have zombies left. So we have 600 zombies. You might be getting the idea, but let's try one more example. Let's say that you're on winter break and you watch 3 movies per day for 10 days. Well, that means you're going to end up watching 30 movies. And again, our units are days in this case, and they cancel out, leaving us with just movies. So our formula up here, that's what we're going to use in this problem. Usually it's written a different way. Usually it's written with distance first. So we have distance equals rate times time. So essentially, you are doing something at some speed. You are doing it for some amount of time. And after that time, you have gotten some total amount. So whether it's driving or shooting zombies or watching movies, this formula applies. As long as we have a rate and a time, we can find some total amount or distance. Okay, before we use this formula, how about we visualize this problem? So it says that during the first 3 hours, Andy drove 40 miles per hour, and then he drove another speed for the last hour. So let's try to visualize that. Let's imagine he's starting at this dot. He drives a certain distance. Let's call this distance d with a subscript 1, which means this is the first distance. So this was for the first 3 hours. And then he drives a different speed for the final hour. Let's call that distance d sub 2 for the second distance, and that's just going to be 1 hour. And let's call this total distance d sub total. So the d stands for distance, and these subscripts, they are just labels to help us understand this problem a little better. We have our first distance, our second distance, and we can consider our total distance. So this picture here represents our problem, and let's use it to come up with some equations. So what do we know about our total distance, our d subtotal? Well, we know that our total distance equals our first distance plus our second distance. We also know that our total distance equals the rate that we drive it times the amount of time that we drive it. So this is using our distance equals rate times time formula. And we're told in our problem that Andy's average driving speed for the 4-hour trip was 45 miles per hour. So overall, for his 4-hour trip, we say that he drove 45 miles per hour. So we can write that in here, 45 miles per hour. And how long was his trip? His trip was 4 hours. And now we have the pieces we need to find the total distance. 45 miles per hour times 4 hours allows our units to cancel. And 45 times 4 is 180 miles. So that is the total distance. All right, we're starting to fill in the pieces of our picture. So let's consider our D1. What can we say about that? Well, we can use our same formula. Our first distance is equal to the rate that we're driving times the time that we're driving. So what is our rate or our speed during that first distance? Well, they tell us that during the first 3 hours, he drove 40 miles per hour. So we can put that in here. 40 miles per hour. And how long was he driving? We already have that in our picture. 3 hours. And multiplying 40 miles per hour times 3 hours gives us 120 miles. So now we know our total distance and our first distance. So we can actually use our equation up here and solve for D2. So our total distance is 180 miles, and our first distance was 120 miles. So we just have D2 defined. How do we do that? We subtract 120 from both sides. We want to get D2 by itself. So 180 minus 120 gives us 60. And 120 minus 120 cancels out, and we're just left with D2. So our second distance is 60. Okay, so we filled in all of our pieces in our picture. So let's take a second to review what they're asking for. They're asking what is the average speed for the last hour of his trip. So last hour of his trip would be the D2 area. So average speed is another way of saying rate. So they're asking what was the rate for the last hour of his trip. Well, you see the word rate, so first thing that should come to mind is distance equals rate times time. We know our D2 is 60 miles. We don't know the rate. That's what they're asking for. And how long was he driving that second distance? 1 hour. So we want to solve this for our rate. So we're going to divide both sides by 1 hour. On the left side, 60 divided by 1 is just 60, and miles divided by hour is miles per hour. And on the right side, we can see that our 1 hours cancel. So we're just left with our rate. So the rate, or the speed that he was driving that second distance, is 60 miles per hour. Looking at the answer choices, that would be option B. So when you see problems talking about average speed or distances, you're most likely going to need this formula, distance equals rate times time. And it might take some time to get to the answer. As you can see, I started off by drawing a picture and then jotting down some useful formulas. And then step by step, I was able to fill in parts of that picture and then get to our answer.